Now we're going to break down vectors in terms of their components. We'll start in 2 dimensions. It's a bit like your x and y axes in coordinate geometry. So I'm going to introduce 2 vectors, 1 unit in length each. There's I, which is in the x direction, or along the x-axis, and j in the y direction. And these both have length of 1. And we can now express other vectors in terms of these unit vectors. So let's say we have 2 points in the plane, O and P, and we have a vector, OP, that gives the position of P relative to O. That's what we call a position vector. We can break this vector down into its components in the x and y direction. It's the sum of a vector A directly across in the x direction and another vector B straight up in the y direction. So OP here is equal to A plus B. So we've broken it down into a vector in the x direction and a vector in the y direction. Now if we say that the length of A is just A, the length of the vector A is just the number A, or the scalar A, and the same with B, well, since A is in the same direction as I, and I has length 1, that means that A, the vector, is equal to A times I, the unit vector in the x direction. And the same for B. B is equal to the length of B times J, the unit vector in the y direction. So now we can break down OP in terms of I and J. OP is equal to A times I plus B times J. So this is really just like x and y coordinates, except that instead of x and y, we're using our I vector in the x direction and our J unit vector in the y direction. The length of OP in terms of the lengths of A and B can be found with Pythagoras' theorem. So we know that for a triangle with a right angle here and sides A, B and C, Pythagoras' theorem tells us c squared is equal to a squared plus b squared. Now in this case, A and B are just A and B, the lengths of those two sides, and C is equal to the length of OP. So the length of OP squared is equal to A squared plus B squared. And so the length of OP is equal to the square root of A squared plus B squared here. Now for vectors in 3 dimensions, we do the same thing. So we have our I unit vector, a vector of length 1 unit along the x-axis, J, the unit vector in the direction of the y-axis, and we introduce K, which is the unit vector along, this is a typo, the z-axis. So if x and y are on the page like usual, or I and j, then the z-axis, or the direction of the K unit vector, is going to be coming straight out of the page. So we can't really draw it there. We can try and rotate this whole thing around a little bit and try and draw this 3D thing on the 2D page, something like that. It doesn't quite capture it. But on the left, just remember that your K vector here is coming straight out of the page into 3 dimensions. Kind of hard to draw. If a point has coordinates A, B, C, that means that in 3D space it has x coordinate is A, the y coordinate is B, and the z coordinate coming out of the page is C. Well then, to write the vector OP, where O here will be the origin, the vector that goes from the origin to the point P with those coordinates is OP, and it can be broken down like this in terms of the unit vectors. A times I plus B times J plus C times K. So we've just added in a 3rd dimension there in the z direction with the unit vector K. The magnitude of the vector OP is very similar to the 2-dimensional case. It's the square root of A squared plus B squared plus C squared. So let's try some of these examples. So the first one asks us for the length or the magnitude of the vector A, where A is equal to 3i plus 4j minus 12k. So here the length of A, the magnitude of A, I should say, is equal to the square root of 3 squared plus 4 squared plus 12 squared. Now it's plus 12 squared and not minus 12 squared. So that's 9 plus 16 plus 144 square root is equal to the square root of 169, whatever that is. What about the length of A plus B? Number 4. Well, A plus B itself we get by just adding up all those components. So A is 3i plus 4j minus 12k plus B, which is just I plus 12k. So now we add up all those components. We have 3i plus I is 4i. We have plus 4j. And we have minus 12k plus 12k. So that's 0k. I needn't even write that down, but I will just to be clear. So the length of A plus B then is equal to the square root of 4 squared plus 4 squared is equal to the square root 16 plus 16 square root of 32. The last thing we look at today is unit vectors. So a unit vector is a vector with magnitude equal to 1. And so here they say if A is some random vector with magnitude of A, then this little symbol here with the hat, A hat, that's the unit vector in the same direction as A. So it has the same direction as A, but magnitude 1. And the way we get it is we take our vector A and we divide it by the magnitude of A, so that we end up with magnitude 1 in our unit vector. We could also define a unit vector in the opposite direction. And that would just be minus A divided by the magnitude of A. So let's do an example. Here we have A is equal to 1, 2, 3. What that means, this notation A equals 1, 2, 3, in terms of unit vectors, it means that A is equal to 1 times I plus 2 times j plus 3 times k. That's what that 1, 2, 3 in brackets notation means. So the first thing we're asked is to find a unit vector A hat in the same direction as A. So first we're going to need the magnitude of A, and that's just equal to the square root of 1 squared plus 2 squared plus 3 squared. It's equal to the square root of 1 plus 4 plus 9 is equal to the square root of 14. And I'll just leave it as the square root of 14 for now, instead of trying to write it as a decimal. Then, to get the unit vector A hat in the same direction as A, that's equal to A divided by the magnitude of A, which is just A divided by the square root of 14. So in terms of components, that is A hat is equal to I plus 2j plus 3k all divided by the square root of 14. Or component by component, that is 1 over the root of 14 times I plus 2 over the square root of 14 times j plus 3 over the square root of 14 times k. And that'll do. You could write these numbers out as decimals if you want. That'll do for now. And that's good, because that's the answer that we're given here. What about a unit vector in the direction opposite to A? Well, we already have the one in the direction of A. So the one opposite to that, we'll just change the sign of everything. So it's minus 1 over 14, minus 2 over root 14, and minus 3 over root 14. Finally, a vector of magnitude 5 in the same direction as A. Well, we just got a vector of magnitude 1 in the same direction. So if we want to multiply that magnitude by 5, we take our vector with length 1, which we got in part A, and we just multiply it by 5. So that's the solution for part C, a vector of magnitude 5 in the same direction of A. So that's the nice thing about unit vectors, is that you can get a unit vector in a particular direction, and then you can get vectors of various lengths or various magnitudes in the same direction as the one you started with. So that's unit vectors, and we'll leave it there for now.